Hi, this is Mark Miner, and my partner Sam and I decided to do a project over ranking F1 drivers and teams using optimization.
All right, so why F1? Because it's competitive, awesome, and there's a ton of data out there to play around with. We decided to try and rank each driver and team somehow. Now, technically, you could just go to F1's official website where they tell you who's the best. They already have their own ranking system that they use for ranking, but we didn't like how they calculated it since it's not entirely performance related. Instead of ranking drivers using concrete winning data, accounting for certain factors, they stole their idea from Mario Kart. In each race, drivers get points based on their finishing position, add them up over the season, and boom, you have a ranking system. We saw this and decided to make a project out of it. Using optimization, we wanted to rank drivers not by luck or a standard point system, but by actual long run consistency. Which drivers actually are the best at the end of the day when you size all of them up individually. Initially, gathering data was a meticulous process, but we managed to get data for all 24 races from 2024, and we shaped the data set the way we needed. Each row represents one driver in one race showing their team, name, finishing position, and track. But raw text is messy, and our mathematical model wouldn't be able to read English. So we gave every driver a unique ID, every team a unique ID, and every track a unique ID. This made our data much more possible to feed into a model since it's in a numerical form.
This slide shows the mathematical formulation of our original optimization model, which ranks all F1 drivers from our dataset that we chose, based solely on their finishing positions across the season's races. We begin with our core sets. So we have R, which is the set of the races in our dataset that includes the full 24 race calendar. D is representative of the set of drivers, and we ended up having 24 total, which we can explain here in a second because we only meant to gather 20 from each race, but we'll come back to that. And then K represents all possible final ranking positions from 1 through, the max of D, which is 24. Next, we introduce our key parameter PDR, which stores the finishing position of each driver in each race. This is the raw input data the model uses to infer the overall performance of each driver. XDK is a binary variable that assigns each driver to a unique final rank. P of D captures the final ranking assigned to each driver, and YRIJ is another binary variable used to track whether driver I finished ahead of driver J in race R. The objective functionally simply minimizes the total number of ranking violations. In other words, if the model ranks driver I ahead of driver J, but J actually beat I in the majority of races, that counts as a penalty. The model tries to minimize all such inconsistencies. The constraints enforce 3 important requirements. Each rank can only be assigned once. Each driver must receive exactly 1 rank. PD accurately reflects the rank assigned by XDK. The final constraint uses a big M formulation to link how the model interprets head-to-head performance between drivers. Altogether, this model finds a ranking that is as consistent as possible with the actual race results. This slide showcases how the data is structured in AMPLE. On the left, you can see the full list of drivers included in the model stored as a simple AMPLE set. Although our dataset contains results for only 20 drivers for each race, the full field consists of 24 drivers, which is what I was mentioning earlier. This is due to reserve drivers stepping in for primary drivers during certain events, which results in incomplete race participation. We include all 24 to maintain an accurate and complete ranking for all the drivers that we have considered. On the right, we have the core parameter table, the matrix position, where each row corresponds to a driver and each column corresponds to a race from 1 to 24. The values represent the finishing positions. For example, Max Verstappen's row contains almost all 1s, which should intuitively push him to the top of our final ranking. This data feeds directly into our objective and constraints. Anytime the model compares 2 drivers, it references this matrix to determine who actually finished ahead of whom. So this slide essentially shows the real-world F1 results transformed into the mathematical form the optimizer can interpret. The following is the final ranking that our OR model produces. As expected, Verstappen ranks first, followed by Norris, Piastri, Leclerc, and Sainz, rounding out the top 5. What is interesting is that this ranking can differ slightly from the official Formula One standings because our model is not based on points, it is based strictly on finishing positions and consistency in head-to-head matchups. So instead of using the F1 point system, we are generating a mathematically consistent ranking based on pairwise results across the season. This slide confirms that the model is working as intended and produces intuitive, data-driven rankings. After building the driver-level ranking system, we extended the model to evaluate team performance as well. The idea is, instead of ranking individual drivers, we now want to rank the 10 Formula One teams based on how their drivers performed. To do this, we needed to add a new set, which we called T, which is representative of the set of teams 1 through 10. We also introduced another parameter, A of DT, which maps each driver to the team they race for. This comes directly from the team of parameter in AMPL, which is what we called it. The key change in this model is that instead of the variable x of dk, we now use x of tk to assign each team to a final ranking. The objective and constraints follow a similar structure as before, but with an added rule. We only compare drivers across different teams, so if 2 drivers are on the same team, their internal ranking doesn't count toward team performance. The big M constraint at the bottom ensures that if team I's driver consistently finishes ahead of team J's driver, then team A should receive a better rank in the final assignment. This extended model gives us a mathematically justified ranking of teams grounded in their drivers' collective results. The following shows the additional parameter and sets required for the team-based model. On the left is the list of all 10 teams included in the analysis. On the right, we have the team of parameter, or the A of DT, which maps each driver to their correct constructor of team. For example, Verstappen and Perez belong to Red Bull, Leclerc, Sainz, and Behrman belong to Ferrari, and so on. This mapping is essential because it allows the optimizer to translate individual driver results into a single aggregated ranking for each team. These parameters make the extended model possible by connecting the driver-level performance data back to the team that they race for. Finally, this slide shows the results of running the team-level ranking model. The optimizer ranks Red Bull as the top-performing team, followed closely by McLaren and Ferrari. Mercedes comes fourth, and Aston Martin rounds out to the top 5. Again, this ranking may differ from the official Formula One team standings because our model looks at consistency and relative finishing performance rather than the actual point system. What this tells us is that our mathematical formulation is capable of generating an interpretable, data-driven team ranking based on the combined performance of individual drivers. Together, these results give us 2 distinct but connected rankings, one for drivers and one for teams, both generated entirely through optimization.
Some key takeaways from this project were that pairwise comparison models lead to accurate rankings. By this, we mean it makes more sense. It handles certain values that are just the result of variability, like DNFs and things like that, a lot more accurately, and more on that in a second. But another key takeaway is real-world data is messy and requires careful precision. When we initially loaded in our data set, it was all over the place. Like we had numbers, texts, all sorts of different formats, and we needed to take that and make it work with a mathematical model. So it required quite a bit of fine-tuning and cleaning, and that's something that we learned about this project specifically, is that it required a lot of data handling and manually typing in values, basically. Another key takeaway, and the last key takeaway, is race-by-race variation highlights the need for aggregated metrics. Like I said a second ago, this model handles DNFs, which is did not finish, and other factors like that in a very accurate way. So just because a racer did not necessarily finish the race does not mean that they're the worst driver. It means that maybe there was a problem with the car or the track or even the driver having a bad day. The point system that arbitrarily assigns every driver a point for the position they finished in is not accurate because it does not handle these things without penalizing heavily variability. In the future, this model can be extended further to basically just analyze team performance for the future using the established pairwise hierarchies to forecast outcomes. And it can be used to predict these things.